Imagine an atom. It's resting quietly in its ground state, like a pendulum at the bottom of its swing. But we don't want it to stay there. Whether we're building lasers, performing quantum logic, or controlling molecules, we often need to move that atom into an excited state. This process, population inversion, is a building block of modern atomic and molecular physics. But here's the challenge. How do we do this coherently? That is, how do we transfer population without loss from decay, or dependence on exact pulse areas or resonance conditions? This becomes especially important when the necessary intermediate state is short-lived and subject to spontaneous emission. This is where STIRAP, or stimulated Raman adiabatic passage, comes in. It's a technique that allows near-perfect population transfer between two states without ever significantly occupying the intermediate lossy state. Before introducing STIRAP, it's instructive to consider why two-level systems fail to enable robust and complete population transfer in many settings. When driven by broadband light, population dynamics are governed by the Einstein rate equations. Even under strong illumination, detailed balance enforces symmetric transition rates. The excited population saturates at 50%, and inversion cannot be sustained. Under monochromatic driving, the system exhibits Rabi oscillations. A pulse with area pi can, in principle, transfer all population to the excited state. However, the process is highly sensitive to experimental imperfections. Errors in intensity, detuning, or timing distort the pulse area, and spontaneous emission during evolution through a short-lived excited state introduces decoherence. Averaged over trials, coherent excitation leads to significant loss in fidelity. We will see later how adiabaticity allows for a more efficient inversion. To circumvent these limitations, a three-level system is introduced with a lossy intermediate state 2 and two long-lived states 1 and 3. The system is driven with two coherent fields, a pump field coupling 1 and 2, and a Stokes field coupling 2 and 3. This setup is necessary because in many atomic and molecular systems, the initial and target states 1 and 3, such as two metastable or high-lying levels, are often not directly dipole coupled. That is, the dipole matrix element vanishes due to parity or angular momentum selection rules. To bridge this gap, we use a real intermediate state 2 that is dipole allowed and hence strongly coupled to both 1 and 3. However, this strength comes at a cost. Such states couple efficiently to the electromagnetic vacuum and decay rapidly via spontaneous emission, making them highly lossy. Let's set the stage with a simple three-level atom. We'll call the states 1, 2, and 3. The key idea is that state 2 is short-lived. It decays rapidly via spontaneous emission. So while we'll need it to mediate transitions, we'd like to avoid spending too much time there. To control the system, we introduce two laser fields. A pump laser couples 1 to 2, and a Stokes laser couples 2 to 3. These fields oscillate with their respective carrier frequencies, omega p for the pump and omega s for the Stokes, and we'll describe them with time-dependent Rabi frequencies. Now, under the rotating wave approximation, which drops the rapidly oscillating terms, we can write the Hamiltonian in a much simpler form. It's a 3x3 matrix with time-dependent couplings between the states, and the detunings delta p and delta s that account for how far off resonance the lasers are. But if we tune the lasers just right, so that their detunings are equal, the Hamiltonian simplifies even further. This is the form we'll use to understand how population moves through the system, and how we can cleverly guide it along a path that avoids decay entirely. Now that we have our Hamiltonian, let's see what it tells us about how the system evolves. When we diagonalize it and find its eigenstates, we get a special eigenstate that lives entirely in 1 and 3, with no component in the lossy state 2. This is the dark state, a coherent superposition. The mixing angle depends on the relative strength of the pump and Stokes couplings. As the laser pulse evolves in time, this dark state smoothly rotates, guiding population from 1 to 3 while entirely avoiding 2. As long as the system follows the state adiabatically, and the pulses are applied in the correct time order, the dark state remains an eigenstate with zero eigenvalue. Once we've identified the dark state, we can now ask, how do we move the population from 1 to 3 along that path? The adiabatic theorem tells us that if the Hamiltonian changes slowly compared to the energy gap between the eigenstates, the system will stay in the same eigenstate. To find the condition in terms of the mixing angle, we start with the time-dependent Schrödinger equation in this instantaneous eigenbasis. Let's suppose the system starts in the dark state A0. The question is, what's the amplitude to leak into a neighboring eigenstate like A1? This is given by an inner product which, for STIRAP, is most relevant between the dark state and the nearest bright state A1. Since the dark state depends on the mixing angle, and the mixing angle is the ratio between the Rabi frequencies, we can compute. The energy gap between the dark and bright states is still. So the local adiabatic condition becomes This inequality ensures that the time evolution is slow enough for the system to remain in the dark state throughout the process. In experiments, this condition guides how to shape and delay the laser pulses. Finally, there's also a useful global version of this condition. It tells us that the product of the effective Rabi frequency and the pulse duration should satisfy. This gives us a simple rule of thumb. If the pulses are strong and long enough, the system has time to follow the dark state and complete the population transfer. Now that we understand the mechanism, how can we confirm that STIRAP is responsible for population inversion? To answer this, we measure the transfer efficiency as a function of the overlap delay between the pump and the Stokes beams, while keeping all other parameters fixed. When the Stokes beam is shifted far upstream so that it doesn't overlap with the pump, population is only driven by the pump laser to the intermediate state. Some of this leaks into 3, but most is lost. This gives us a baseline. As the overlap increases, coherent coupling takes over, and the system begins to follow the dark state. The result, a sharp rise in transfer efficiency, which eventually flattens out into a broad plateau. This plateau is the STIRAP signature. Maximum transfer occurs near optimal overlap. Efficiency drops off on either side, but remains high across a range. This kind of robustness is strong evidence for adiabatic passage through the dark state. STIRAP exemplifies how coherence and adiabaticity can be harnessed to achieve controlled population transfer in open quantum systems. By evolving the system along a time-dependent dark state, an instantaneous eigenstate with zero population in the lossy intermediate level, we bypass spontaneous decay entirely. This protocol converts an unstable 3-level configuration into a robust, high-fidelity 2-state transfer channel, as long as the adiabatic condition is satisfied.